is kind of weird because it's sort of like a counterintuitive concept. All right. So anyway, the objective: identify sets and operations under which they're closed. Identify properties of real numbers. All right. So those properties, you got your commutative property, associative property, identities, and all that good stuff. So we'll cross that bridge in a little bit. But the do now, state whether the set is closed under the indicated operation. If it's not closed, give a counterexample. All right, so you have this whole blurb here of, related to what makes a set closed. All right, but I'll give you the gist of it here. So a set is closed if the result of an operation gives only results in the original set. Well, I'm using results too frequently there, so I'll say values. Penmanship's a little out of whack here. Hold on. Only values contained in the original set. I'll zoom out in 1 sec. All right. So a set is closed under an operation if the result of an operation gives only values contained in the original set. So that isn't going to mean a whole heck of a lot right now, but it will in a minute. It's a perfectly straightforward concept. The problem is it's not the kind of term that necessarily lends itself to its definition. All right, so sometimes you know what a word means just based off of the word itself. All right, so this a case could be made for that, but it's kind of wishy-washy. All right, so I'm going to take you through an example or a set of examples where we talk about this concept of closure. But I'm not going to start with number 1 because it's kind of weird, but the simpler the set, the more confusing this concept of closure is. All right, so I'm gonna go with something that's a little bit more elaborate. So we'll actually work backwards through this set of examples. We'll work with number 6 first. All right, so we have 1, 3, 5, and so on. All right, so the ... this ... is telling us that the trend continues to the right, but there is no ... preceding the 1. So that's telling us that this set actually starts with the number 1, then increases by odd integers from there, but it doesn't go back in time. You're not going to see -1, -3, or anything like that. All right. So what we're going to do here is we're going to multiply, because this is the operation, multiply any 2 values in this set. Now it's infinite, so that could take a while if we don't do this the right way. All right, so multiply any 2 values in the set. If the result is in the set, so if the result is a value in the original set, then the set is closed. All right, but specifically closed under the operation of multiplication, but that's a lot to write. All right, specifically related to multiplication. All right, so now there are infinitely many values between 1 and infinity. So they're all odd though. So what I'm asking myself is, can I multiply any 2 values from this set So from the set of positive odd integers, can I multiply any two values from the set of positive odd integers and end up with a value that is only going to ever be a positive odd integer? All right, so what I might do is I'll choose something like 1 times 3. That's 3. Okay, 1 times 3 is 3. 3 is a number that's contained within the set. I see it right here. All right, so that one works. So I just have infinity minus 1 more to go. Right? Because I got one pairing down. Now I just got to do this, infinitely many more times. I forgot to tell you that this whole course is just this one problem. We're going to do this one problem for the rest of the year because that's how long it takes. If we do infinitely many pairings, it'll take longer than this course. It'll take the rest of your life and then the rest of everybody else's lives on top of that. All right? So that's not going to work. So what we look for is what we call a counterexample. A counterexample is a case that doesn't work. All right? Because if we get one instance where we don't meet with success, then we will have disproved the rule. All right? So we're not looking to prove, we're looking to disprove. All right? So, and the bottom line is if we can't come up with a counterexample, then we're looking at something that is going to be true. All right? We will have proved, we call it indirect proof. All right? So I might try another example like 3 times 5. All right, so these are my examples. 3 times 5 is 15. So I look at my set, I don't see a 15 there, but the ... tells me that trend continues. So this is really telling me 1, 3, 5, 7, 9, 11, 13, 15. I'll do a couple more, 17, 19, 21, and so on. All right. So the odd values will continue. So based off of that, I can come up with another value, maybe 7 times 9. 63. Once you recognize that this is the set of positive, I'll write the word positive, odd integers, you kind of streamline things a little bit because now you're thinking, all right, I'm going to multiply any two odd numbers together. Will the result that I get always be odd? Right? Because the odd set of integers, positive integers, is that set that they gave us. All right, so I would say, all right, well, let me think of something funky. All right, how about 79 times 6,351? All right, so those are two odd numbers. So I'll multiply them. The result is odd. It ends with an odd number, so it's going to be odd. So 501729. I can't think of anything else. I mean, there's a lot of different possible pairings, but I can't think of anything that's going to bring anything more to the party than what we have here. I can't incorporate an even number. Right? I can't get a 0 in there. That's not part of the original set. I can't use negatives. So what we would say is, I'm looking at all these answers here. I'm seeing odd, 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 odd. I can't think of any possible pairing that's going to give me an answer that's something other than odd. All right? So what we would say is the set is closed under multiplication. All right, the set is closed under multiplication. But it might not be closed under addition, subtraction, or some other operation, division. You could have operations that involve powers. Any kind of manipulation that you perform on a number is an operation. All right. So any kind of transformation, sometimes it's just a simple matter of negating it, like popping in a negative or removing a negative. That's an operation. All right. So let's go back to number 5, 2, 4, 6, 8, and so on. So those are the set of positive even integers. Now it's talking about addition. So if I add any two, so add instead of multiply, any two even numbers, will I get a result that's not even? All right. So maybe you try a couple of examples. You think about 2 plus 4. Then maybe you do 6 plus 8, and then you do a funky one. All right, maybe that funky one is 6,560 plus 4,242. All right, two even numbers added together, positive. All right, 6, 14, and I'm sure I could figure it out in my head. I just don't want to. Oops. Probably could have figured it out before I type it in, though. 10,802. All right. So this is the set of even integers, set of positive even integers. So it would be closed if under addition, my result is always going to be a positive even integer. I can't think of a single case where it would be something other than that. So the set is closed under addition. All right, set is closed under addition. So let's do one where it's not necessarily closed. So 2, 4, and 8. Now, you don't see dot, dot, dot here. All right, so this just got a little bit more interesting. Also, it's what we call finite. All right, this is a finite set. One of the challenges in math is getting a handle on the vocabulary. Not because there will be a direct question related to it. It's that when you understand the vocabulary, when people speak to you in mathese, you'll know what they're talking about. So 2 or 3 years from now, when you have a teacher that speaks to you using mathematical terminology, you're not looking up the terms as the teacher is explaining concepts. You'll have an idea. So when I say a finite set, you're like, oh, is that going to be on the test? Is it a vocabulary word? No, it's not going to be. Just you want to know it. All right. The other one is an infinite set because of the dot, dot, dot. All right. So what we are looking for here, in order to establish closure, is any value through division, or any pair of values through division, should not result in anything other than what you see here. All right. 2, 4, and 8 are the only possible answers that we're looking for. If we get something other than a 2, 4, or 8, then it's not closed. So I look at this as like, I mean, you'll see the little blurb here, but I kind of look at the 2, 4, and 8. They're the guest list to a party. All right, yeah, you see it in the movies. I've never experienced this in real life, but you go up to the front door for a party, and there's somebody there. They're like, "Are you on the list?" And you say, "Yes, I am," even though you're not. You know, like they do in the movies. But this is the list, 2, 4, and 8. So through division, if I operate on any pairing of these 3 values, will I ever get something other than 2, 4, or 8? Well, it depends on the order. Because, for example, I could say 8 divided by 4 is equal to 2. That's part of the set. That works. But what about 4 divided by 8? That's 1/2. This is not part of the set. Not part of the given set. So the set is not closed or open under division. So I'll say the set is not closed. All right, and that's because we got what we call a counterexample. That counterexample is the one case, it could be more than one, but one case where the rule doesn't apply. So I wanted closure, that's my rule, quote unquote rule. This is the one case or one of the cases where I don't get closure. All you need is one. Then the whole process fails. All right. So 0, 2, negative, I just pretty much gave away the solution. 0, 2, and 4. This, I'll tell you right now, this one will not be closed under subtraction. It's a finite set, 0, 2, and 4. Can you give me an example, a counter example that shows that it will not be closed?
0 minus 2.
Exactamundo. So the example, 0 minus 2 is negative 2, not part of the set. So it's not closed under subtraction. So not closed. All right. Zero and 1 under multiplication. Would we say that that's closed or not closed? It's finite set. Can you think of any ways in which you can multiply the number 0 and or 1 and get something other than 0 and or 1? No, this is going to be closed. All right, you'll notice in each case, I'm not just writing closed or not closed. It's closed under an operation. Because if I said 0, the set of 0, 1, but I use subtraction, it's not closed. Because 0 minus 1 is negative 1. That's not part of the original set. All right, so you got to be specific. All right, that's where the writing part is going to come into play. All right, not too much. I mean, you see here I wrote an essay, but here I used a lot of abbreviations. Somewhere in between those two is where you should be living. You know, don't abbreviate too much, but you don't have to write a narrative either. All right. The reason why I was so, lengthy with number 6 is because I was teaching it a concept. All right. You don't have to teach me the concept when you write an answer for the test. All right. Just get the idea across and you're good. All right. 1 through multiplication, would that be closed or not closed? Yeah, that's going to be closed. If you multiply 1, you're like, oh, there's nothing to go with it. Well, you could repeat numbers. So 1 times 1, is 1. Like if you wanted to do it with division, it would also work because 1 divided by 1 is equal to 1. So this is closed under multiplication. All right. So all the remaining problems, they're just practice of this concept. All right. So, in terms of identifying like the solution to, let's say, number 4 on page 8, you're looking at kind of a mixture of concepts. You got to know what natural numbers are, whole numbers and rational numbers, in order to be able to tackle these kind of questions. All right. Same idea with page 9. All right. So page 10 is a little bit more like what we were just doing. And then we get into applications, which is page 11 and 12. We're going to sit tight on that. You don't have to worry about that. But we're going to complete through page 10, or at least try to. You don't have to do them all. When it comes to homework, you never have to do them all. It's just that, you want to get good practice. So tackle ones that, they look kind of challenging. If you know that you know how to do something, then don't bother with that one. Do the ones that you think you might have trouble with. All right. So we're looking at, again, pages 8 through 10 for classwork/homework, because we're 6 and 7 we're going to come back to down the line.
So So 8 through 10 is homework.
8 through 10, yep. Yeah, 8 through 10. And I'll put that up on Schoology in a minute.
Is it okay if I have some of the work in my phone? So when I go home, I like to print out that sheet